Hello everyone, my name is Soran Parsa and I am a research fellow at the University of Lincoln, and I am going to present our work on haptic guided shared control grasping for collision-free manipulation. Teleoperating of a manipulator is the main means of performing a task in conservative domains such as surgery and aerospace, and also in extreme environments such as nuclear power plants. Teleoperation is not intuitive and imposes a lot of cognitive load on the operator. To perform this operation, operator performs a sequences of grasp, move, and then maybe drop the object because it is close to a joint limit or collision situation. This sequence of grasp, move, and drop result in fatigue and degeneration in performance. In addition, there are different robots' dynamic and kinematic states that are not intuitive for operator, and operator is not aware of them while they are happening. For example, joint limits, kinematic singularity, joint velocity, and joint torque limits are not intuitive for an operator and they are not aware of them unless there is an intuitive feedback such as haptic or VR feedback. There are different applications such as suturing in robotic surgery that haptic feedback was used to inform the operator of joint limits and singularity. In this operation, when the robot reached joint limit or singularity, the operation dropped the needle and tried to grasp it in a better configuration. In this application, a 2D manifold was defined around the needle and force Q were generated based on the distance from joint limit and singularity. One limitation of this approach is that it provides just one single global grasp configuration, and haptic forces inform the operator of that global grasp candidate. Another application of force cues in terms of haptic feedback was used to maximize the kinematic manipulability along the entire post-grasp trajectory. In this method, the operator handles the reach to grasp phase, while the post-grasp movement is performed autonomously. One of the limitations of this method is that this method increases the cognitive load due to destructive force cues in some cases. In this research, for a given post-grasp object trajectory, here shown as a green line, we aim to find a good initial grasping configuration whose corresponding end effector trajectory allows the inverse kinematic solver to produce a collision-free path. We assume that the object is perfectly rigid and the connection between the sole slave arm and the end effector is stable. Also, we assume that once the stable connection is made, the end effector frame becomes equal to grasp pose frame. We used collision costs to generate haptic feedback to inform the operator of potential post-grasp collision. For instance, in this picture, this head-shaped object is supposed to be grasped. If the object is grasped from this horizontal part, it results in collision. But if it is grasped from this vertical part, it is collision-free. Operator is not aware of this potential collision before it performed the grasp operation. We used haptic feedback to inform the operator of potential post-grasp collisions. In order to generate haptic feedback, first we need to compute collision costs. To compute collision costs for a specific post-grasp trajectory, which is shown using this equation, first we need to obtain joint space trajectory of slave arm using inverse kinematic solver. Then we need to assign body points to our robot arm, which are denoted by this equation, and compute post-grasp trajectory for robot body points. We represent obstacle using linear constraint as shown in this equation. At the end, collision cost is a function of grasp candidates, object trajectory, and obstacle pose and shape. The aim is to minimize this function. We used two different strategies to generate haptic feedback. First strategy was classical bilateral force feedback, and we designed our controller as this equation. This controller consists of two terms, which the first one is the damper term, and the second one is the ratio of cost gradients. The concept of the controller can be seen as this block diagram. First, we obtained the point cloud of the object and obstacle using a real sense camera. Then we synthesized the grasp candidates using a general grasp point generator algorithm. Finally, collision cost and cost gradients are calculated and are fed to a PD controller to generate the haptic feedback torques. Using this strategy, there are situations that the produced haptic feedback is not in line with the direction of the motion. For example, the direction of the force Q is different from the direction of the motion, or even the direction of the force Q is opposing the direction of the motion and resists the operator. To address this problem and mitigate this effect, we propose different policies and compare them together. For example, in policy number 3, we made the tangent element of the haptic feedback along the direction of the motion attractive. Or in policy number 4, we cancel the tangent element of the haptic feedback force Q along the direction of the motion. Our experimental setup consists of two panda arms that are connected as a master arm and slave arm. The slave arm is controlled as a compliant and follows the configuration of the master arm. We used Franca control interface as a low latency communication and control between master and the slave arm, and also a real sense camera which used to obtain object and obstacles point cloud. We proposed two different pick-and-place tasks to test our strategy and policies. First task is a straight object, and it is supposed to grasp from a grasp point and placed at the end point. The second task is an head-shaped object, and it is supposed to pick and placed in an endpoint behind the obstacle. Then we calculate the time to completion of the operation as an important factor of the haptic feedback operation to compare the different policies, which can be seen in these two graphs. Based on our experiments, we observed that the force cues are noisy, which increases the time to completion of the operation. Also, due to high load of the computation, the haptic force cues frequency is low, that reduces the quality of the feedback. To address these problems, we propose second strategy based on attractive and repulsive forces. For this, we obtained a set of potential grasp candidates and compute collision costs for these candidates. Then grasp candidates are categorized as desired and undesired depending on the median of the cost values. And then based on this categorization, an object is divided into several attractive and repulsive force fields. Based on this illustrative figure, we can see two different grasp candidates on the object. The red point is an undesired grasp candidate, while the blue one is a desired grasp candidate. An attractive force field is generated around the desired point, while the repulsive force field is generated around the undesired point. The end effector is attracted to the desired point, while it is repelled from the undesired one. The controller is designed based on the joint space PD controller concept and as a ratio of normal distribution function of distance between end effector and grasp candidates as this equation. Also, to further reduce the cognitive load on the operator, we divided the area of around each grasp candidate into three different haptic zones. The first one is no haptic zone, where the robot acts as an compliant and no haptic forces are generated. Then there is a transition zone where the haptic force are gradually rises from 0 to full haptic feedback. Finally, at the haptic zone, the haptic controller is fully operated. This diagram shows the three different haptic zones where the haptic feedback rises from 0 to maximum of its value. The block diagrams of the two different strategies can be seen here. For the first strategy, which consists of policies number 2 to number 7, it can be seen that the most of the time-consuming and heavy calculations are carried out online, which reduces the haptic feedback frequency. While in the second strategy, most of these computations are carried out offline, which improves the haptic feedback quality. To compare the different strategies and policies, time to completion of the operations were measured and compared together. Time to completion of the second strategy is shown as P7, which considerably is lower than the other policies. Also, haptic torque produced by different robot joints were measured and presented, from which different haptic zones can be identified. First robots start with zero haptic feedback, and gradually haptic feedback rises to its maximum level. And at this level, it informs the operator of potential post-grasp collisions. In conclusion, we proposed and tested different haptic-guided shared control strategies for teleoperating of a manipulator. Two main architectures for generating haptic forces were developed and compared together using two different teleoperation tasks. Our strategies successfully informed the operator of predicted post-grasp collisions. Also, we improved real-time haptic feedback to reduction of the online calculations to reduce the latency of the control. Also, our modified haptic feedback control strategy led to considerable reduction in time to completion of the operation. Thank you for watching this video. For further detail, please refer to the submitted paper.